Okay, we're into Gay-Lussac. Gay-Lussac, the Frenchman. Or gay, whatever you want to call him. Okay, number one. Okay, so it looks like I have pressures and temperatures. So how do we want to do it? Do we want to do pressures over temperatures, or do we want to do P1 times T2? Let's just keep doing pressure 1 over T1. Maybe it'll be easier for you. So I have a pressure of 1 atmosphere, and it's heated from 20 to 30, so my initial is 20, so that's 293 degrees Kelvin equals, and it's heated to 30, so it's 303 degrees Kelvin, and X atmospheres. Okay, so 1 divided by 293, enter, times 303, enter, X equals 1.03 atmospheres. Again, is it close to the original 1 atmosphere? Yes, 1.03 atmospheres is perfect. So I like that answer. It's not outrageous. It's not a million atmospheres, so let's just go with it. X equals 1.03 atmospheres. And again, all these are just doing the same thing. It's where do I plug it in? I have this at this temperature, right? 0.370 atmospheres at 50 degrees. That means that I have a P1. That means I have a T1. And what is the pressure at standard temperature? So standard temperature is 0 degrees Celsius or 273 X atmospheres. Oh yeah, disobeying my own rule. I wanted to use units everywhere. Okay, do some math. 0.370 divided by 323, enter, times 273, enter, 0.312 atmospheres. X equals 0.312 atmospheres. Again, fairly close to the original. I like that. It's not outrageous. If I could just get you to look at your answers in that regard, at least you could disregard, some bad answers, right? If you get 9 million. Now, other than that one where we got 51,000 liters, because that doesn't make a lot of sense, but, they don't all have to make sense. Number 3. The gas has a pressure of 699, so I have a P1. Doesn't even matter what the units are, as long as they're the same on the other side at 40 degrees. So 273 plus 40 is what? 3, is that 313? Oh, I hope so. 273 plus 40 equals, 313 degrees Kelvin. What is the temperature at a standard pressure? So standard pressure in millimeters of mercury is 670. If you have a problem with that, you can ask me during the test. If you don't remember what a standard is, I'm allowed to let you know. So we need an X degrees Kelvin. So let's see, 699 divided by 313, enter. 670 divided by second answer equals X equals 300.014 Kelvin. So I'm just going to shorten that up to 300.01, but I like that answer. It's fitting with what we have already. It's not too far removed, so 300.01 degrees Kelvin for answer number 3. Answer number 4. Okay, number 4. If a gas is cooled from 323 to 273, ooh, I like that. They've given me my T1 and my T2 without any muss, fuss, or work. Kelvin, that's in degrees Kelvin. And the volume is kept constant. What is the final pressure would result from the original pressure of 750 millimeters of mercury. So I want X millimeters of mercury. And we're off. 750 times 323, enter, times, do you hear me? Do you hear what I'm doing? 750 divided by 323, enter, times 273.15, enter. X equals 634.25 millimeters of mercury. Does it look like it would fit? 750, 634. Yeah, those are close enough, right? I like that answer. So that's the answer I'm going to go with. 634.25 millimeters of mercury. And this is how you get good at this stuff. It's just relentless practice. I mean, honestly, I know it's boring. I know it's not exciting, but it is how you get good at these problems here. Is just by relentlessly practicing and going, okay, 15 atmospheres, and I'm changing it to 16 atmospheres, and the original temperature was 25, which is 298 degrees Kelvin, ATM. The pressure hasn't changed much, so I can tell you this, the temperature isn't going to change much at all. But let's do this. 15 divided by 298, enter. And then what I'm going to do is I'm going to hit 16 divided by second button, answer button, enter. 317.867. X equals 317.87 degrees Kelvin. 298 to 317, not a huge change. I love it. 317.87. 317.87 degrees Kelvin. Okay. Now we're at 6. And I'm running off the page here, so let's just do like this. We'll keep number 5 in frame too, if we can. Yeah, if things fall out of frame, it's because I'm not looking at that camera right there or at that computer right there. I'm looking at this page right here. So if you can't see the calculator, or if I'm covering up the work sometimes, usually I'll get out of the way so that you can see it eventually. All right. We did number 5? We did number 4. What the heck? Is my numbering off? 1, 2, 3, 4, 5. Oh, 6. There we go. So we're looking for 6 right here. Okay, we have 30 liters. Looks like I have a V1. Metal container at 20 degrees Celsius. So 293 degrees Kelvin equals. And then I have a second temperature. 50 plus 273 is 323, right? 273 plus 50 equals, yeah, 323 degrees Kelvin. Was at 3 atmospheres. Oh, they're looking for the pressure, so we don't need a volume at all here. I'm glad I made that mistake. I don't need a volume at all. What I have is was at 3 ATM. So 3 ATM. So I'm going to change this, and then I'm getting X ATMs. They're asking me what is the pressure. Okay, 3 divided by 293, enter, times 323, enter. X equals 3.30 atmospheres, fairly close to what we started with, 3 atmospheres, 3.3 atmospheres. I like that answer. We're going to run with it, 3.3 ATM. Okay, and we continue on. I think I'm going to stop and start another video on combined gas law because that's a good place to stop right there.